Good day, guys. I'd like to return to the astronomical laws and the motion of the planets uh, and the satellites or the objects that are on the universe that are obeying universal gravitational force and they experience this kind of force on it. And before we start, I'd like to say that I will suppose that my satellite is vibrating around the planet at a distance of I will write it as it's the radius, sorry, and this radius is very close to the radius of Earth. So in my calculations, I will suppose that my distance is radius of Earth. Um, of course, when it's vibrating around the planet, for simplicity, I'll take that the our planet is it. Okay, sorry. And when it vibrates, my satellite, it is vibrating with the uh, spatial or the certain speed that's called as tangential speed, and it is on the surface, so that's why it has got its own gravitational field, of course. So I mean that on that orbit, on a certain orbit where the radius is close to the radius of Earth, it will have two kind of energies. First energy that we passed before is called as universal gravitational field or the potential universal gravitational potential energy. I will denote it as EP, and of course, when I calculate the gravitational field for potential energy, sorry, I'll use the minus sign and I will multiply G by the mass of this satellite. Of course, I will suppose that it will have the spatial mass, and I have to multiply it by mass of Earth, and I will divide by the radius, which I suppose that is close to the radius of Earth. So that's why I will write it as radius of Earth. And of course, the second part here, I mean, the second kind of energy that it has, of course, it has got the kinetic energy that is mv square over 2. You know that from the 8th and ninth grade. Now the total energy, of course, will be the sum of these two. That is my kinetic energy. Oh, sorry. Okay, let it be kinetic energy and plus, indeed, I will have the minus sign here. Potential energy that is gm and capital mass of Earth, sorry, and over radius of Earth. So you see here that I have two energies here connected together to calculate the total energy of the satellite at a certain orbit. But I can't add these two because you see here they are not similar. In order to do this, I will suppose that I have imbalance in it. I have two kind of forces here. That is centripetal force and the universal gravitational force. These two are in balance. They're applying on my satellite here, and it's moving with the speed. From the ninth grade, you know that centripetal force of centripetal equals mv square, sorry, mv square over r, where the r is the radius of this orbit when the object is vibrating around the circular path. It experiences the force that is, you see here, that outwards of the radius, and it is mv square over r. On the other hand, I have the gravitational force that we passed before, that is g times m and capital, that's mass of Earth. And here, of course, I have the radius of Earth and radius of Earth square here. So these two are in balance, Fc equals Fg. So I can write here that is mv square over Re will be equal to Gm and capital and the mass of Earth over radius of Earth, but I have the square here. So I can simplify one of them from both sides, and if I divide it by 2, you see here that this meaning here on the left side of the equation resembles me the kinetic energy. So I can write here that it's instead of kinetic energy, mv squared over 2, I can write this meaning here that is on the right side of the equation that gives me g times m and capital E over 2 re, radius of Earth. So my total energy now, instead of kinetic energy, I can plug this expression in my equation. So that's why I will have here that is G times mm capital E over 2 times radius of Earth and plus, indeed I have here the minus sign, G times m the mass of Earth over radius of Earth. So you see here, the only difference here is that I have the division by 2 here. That means that's the half. So my total energy, if I try to calculate it, my total energy, sorry, let me write it here. Now my total energy will completely will change because I have now the certain thing here. Sorry, I have the 2 here, uh, radius of Earth and radius of Earth. So I have here the half and I have the rule here in my mind, sorry. So that's why the total energy that my satellite has is half minus who. So I have here minus g times mass of Earth, mass of satellite, of course, over 2 times radius of Earth. So that will be my total energy gained by the satellite on a certain orbit. Now, in order to just launch it to this orbit, at first, of course, my satellite was at that point here on the surface of Earth. In order to launch it to this orbit, I need a certain speed that I will denote as escape speed. So when I launch it, this satellite here, it will fix on this orbit. In order to fix it, I need a special speed here. So the speed that I need to give to the satellite can be calculated so that my energy that I will use to launch it out, let me write it as kinetic energy prime. So I will have this mass of satellite times the escape speed square root 2. It should be equal to the total energy that my satellite will have on the certain orbit. So you see here, my mv escape square over 2 will have the meaning that is equal to the uh, mean that's given as the total energy. I would like to cancel the minus sign because I don't need it. So in order to calculate the escape speed, so that is, I will try to do it in this way. That's g times mm capital E over 2 of radius of Earth. So I can simplify the 2. I can simplify the masses here. So you see here that my escape speed now will have a new phase that is g times mass of Earth over radius of Earth, and I will have it in root. So what does it give me? It gives me the certain volume. Again, the escape speed is the speed. Let me write it as escape speed 1. The escape speed 1 gives me the amount of speed that I need to launch a satellite from the from the surface of Earth to a certain orbit that will be close to the radius of Earth, and it will move with the speed that is given here. Uh, and it has two kind of energies. That is, it will have two kind of energies as kinetic and potential, and it will move exactly along this path here. Uh, so I can write also the another expression here because that my g times mass of Earth over radius of Earth resembles me a certain amount of g. You know that mg will be equal to g times mass of Earth and over radius of square. So if I simplify the masses, I will have the g here, the gravity, that's a g times mass of Earth over radius of Earth square. So the only thing that will have the difference here, I can write it in terms of gravity. If I put it here, my gravity times radius of Earth in the root will have the same meaning as here. Uh, for example, for my planet here, for our planet, sorry. So these two equations are also valid. You may use any of them. Uh, for example, if I use it exactly for the Earth, I can calculate it easily. The escape speed for Earth will have escape speed. If I plug the numbers instead of letters, I have, I can write it in terms of universal gravitational force, constant, sorry, 6.67 times 10 to the power of minus 11 times the mass of Earth, that's approximately 6 times 10 to the power of 24, and over the radius, that is 6.4, as you know, 10 to the power of 6. Let me deal with the powers first of all. I will have, that is, if the 6 goes upward with a negative sign, minus 17, and that will be 10 to the power of 7. So the number that I will have here, that is 6.67 times 6 and over 6.4, that will give me the number of 6.25 and times 10 to the power of 7. Uh, it will be more easy to convert it to the power of 6, so I can write it as 62.5 times 10 to the power of 6 in root, so that I'll have 10 to the power of 3 out of the root here, so 62.5 in root. I'll have the number that is close to 8, so that will be 7.9 times 10 to the power of 3 meter per second. Again, so that's the speed needed to launch the satellite from the surface of Earth to a certain orbit. Well, I can write it in terms of kilometers, of course, 7.9 kilometers per second. That's the speed that you need to give to a satellite in order to launch it from the surface of Earth to this orbit. Of course, I can calculate the escape speed one. Let me write it as escape speed one. In terms of gravity only, if I plug the gravity in here, that is 9.8. I will write it in more precise value, and times 6.4 times 10 to the power of 6 in meters. Of course, I have to convert it to meters. So 9.8. So the 9.8 I have to multiply by 6.4, and that will give me 62.72. 62.72 times 10 to the power of 6. Sorry. So if I take the root of this, again, it will have 7.9 times 10 to the power of 3. So you see here meter per second. So that will be exactly the same number. So you may find it in terms of universal gravitational constant, mass of Earth, and radius of Earth. And you may also find it in the units of gravity and radius of Earth. These are same things, as you see. Now, if I have the satellite exactly on the distance, of course, on a certain distance, now suppose that I want to just move the satellite from this orbit to infinity, for example, to escape. So I will need the escape speed prime with me, right? Now all I have to do is just to calculate the sum of potential and kinetic energy on that uh, exact orbit, sorry. So now I will write here that r is not close to the radius of Earth, is not close, is not the same. So what should I do? I just write it in terms of, sorry, potential energy, that is gravity times mass of satellite times mass of Earth, and over r here. Uh, and then another thing that I have to calculate is here, of course, I have minus, and I have the mass of the satellite. If it's moving with the speed here, I have to calculate it with the speed square and over 2, so that will give me a certain amount of energy. Again, you see here that I have to calculate now. The only difference here, again, now I'd like to convert the radius. I have to calculate the radius not as the radius of Earth, so it will be a bit different, but the logic is the same. So what you do, the total energy you have to equalize with the energy that we have to give to the satellite. So my escape speed, mass times escape speed, let me write prime over 2 will be the same as the sum of potential energy G times me over radius of, not the radius of Earth, the spatial radius now. It's not equal to the radius of Earth and plus mv squared over 2. And you must calculate this too also. If the certain amount of speed in if the total amount, I mean the certain amount of radius, I mean the altitude is also given. Oh, the things again will be the same. I have here of course the square. Uh, Now let's suppose that I have 30,000 kilometers and uh, now the mass of Earth I already know. And I already know the mass of satellite is given. Now, the only thing that I have to first of all calculate the potential energy between the satellite and Earth. What should I do? I will plug the numbers instead of letters. I have minus g times 6.67 times 10 to the power minus 11 times the mass of satellite, that is, let me write it in terms of 10 to the power 3, and times the mass of Earth, that is 6 times 10 to the power 24, and over the radius, that is 30,000 kilometers. Let me write it in terms of powers here. I have 4 and 10 to the power 7. So my total energy, if I multiply 6.67 by 2, I have here 13.4 minus 13.34 because sorry, I have to simplify. I have to simplify 3 and 6 by 2. And what should I do? Let me deal with the powers here now. This goes upward with the negative sign. It turns to minus 8, minus 18, sorry. 26 minus 18 is 6, and 6 plus 3, that is, uh, sorry, that is, sorry, I lose my numbers here. Now, again, let me write the potential energy. That is minus 6.67 times 10 to the power of minus 11 times 10 to the power of 3 and times 6 times 10 to the power of 24 and over the radius that I've already calculated as 3 times 10 to the power of 3. I will simplify this too, and I have here 13 points minus 13.34 times 10 to the power of 9 as I calculate here because it goes upward with a positive sign. Minus 18 plus 24, um, that will be 6 and plus 3 to the power of 9 joules. But in scientific notation, I have to write the numbers between 1 and 10, so I will write it as minus 1.33 and 4 times 10 to the power of 10, 10 joules. That's the potential energy that is calculated. Now, I have to calculate the kinetic energy of this object here, I mean of the satellite. In order to do this, first of all, I have to find out the speed of this satellite. It has got a certain speed here. So in order to find the speed, I have to equalize the universal gravitational force with the centripetal force that I said before. So my mv squared over r that gives me centripetal force will be equal to the universal gravitational force here over r squared. So my speed here, I will simplify the masses and then I'll simplify one of the radius here. So my speed will be equal g times mass of Earth over radius that is already given and in the root. I have 6.67 times 10 to the power of minus 11 multiplied by 6 times 10 to the power of 24 and over 3 times 10 to the power of 7. So I will have all of this in the root. I will simplify him again. I have the number that's I calculated before, 13.34 times this goes upward and 10 to the power of 6 is present here, as I mentioned, and I will take it in root. Sorry, uh, 13.34 in a root will give me 3.65 65 times 10 to the power of 3 meters per second. So that's the not escape speed, that's tangential speed that I'll have on this radius here. Now, in order to calculate the kinetic energy, I will write mass of satellite times the speed over 2. So mass of satellite is 10 to the power 3. I will multiply it by 3.65 times 10 to the power of 3 in square and over 2. So 3.65, I have to take the square of this. So that is, yes, that is 13.34, of course. So 10 to the power 3 multiplied by 13.36. I don't have to calculate because I already have it here. Times 10 to the power 6 and over 2. 13.34. That's over 4. Over 2, sorry. That's 6.67. 6.67 times 10 to the power of 9 here. Or I can write it mm, in terms of 10 to the power of 10 because I already have it. So my 0.6.67, 67, yes, 667 times 10 to the power of 10 joules here. But I have here the positive sign. So my total energy here, the total energy of the satellite will be the sum of these two, my 1.33 and 4 times 10 to the power of 10 and plus 0.667 times 10 to the power of 10. So the powers are the same. I will deal with the numbers only. 1.33 and 4 minus 0.667. Yes, exactly. That will be the same number. So, but with the minus sign here. The minus sign. So minus 0.667 times 10 to the power of 10 joules. Now I will deal again with the positive number here in order to calculate the escape speed. So to calculate the escape speed, I have to just equalize the escape speed here. Let me write it prime square over 2 with the total energy. So 10 to the power of 3 times the escape speed, the escape square, prime square, sorry, over 2. That will be equal to 0.667 times 10 to the power of 10. So I have here 13. I've already calculated because I have 10 to the power of 3 times escape speed prime square. I have 1.33 and 4 times 10 to the power of 10. So my power goes, this number goes to the right side of the equation. So escape speed prime square, of course, will be equal to 1.33 and 4 times 10 to the power of 7. So that's 10 to the power of 7 is inconvenient, so I have to write it in terms of 6 maybe. So 13.34 times 10 to the power of 6. So my escape speed prime will be equal 13.34 in root. I'll have 3.65 times 10 to the power of 3 meters per second. So that's my escape speed that's required to escape from a certain planet, from this planet here, from this orbit to infinity, sorry, to infinity. So I hope that you understand, but because what we have to do is just to calculate the energy, first of all, the total energy that's given, and then I have to equalize it. First of all, I have to calculate, of course, the potential energy, but with the minus sign, and then kinetic energy. In order to do this, I have to equalize it with uh, the I mean, the centripetal force, I have to equalize with the universal gravitational force so that I can find the speed of the satellite on that orbit. And then I have to calculate the kinetic energy, of course. If I find the kinetic energy, I have to just add these two in one to get the total energy. and then the escape, to find the escape speed, I have to equalize the kinetic energy that you have to give to a satellite to launch and escape from this total energy. I hope that you understand. Mm, So uh, let's try to find out the escape energy that's required to give to a certain object that's exactly on the surface of Earth and to launch it to infinity. You should do? Now it's not moving exactly. We suppose that it's not moving, so the uh, energy, I mean the speed here is zero. So my total energy of the object that's on the surface of Earth can be found as sum of potential and kinetic energy, but my kinetic energy is zero because the speed here is zero. So my total energy is consists of only universal gravitational potential energy, that is minus g times m and the mass of Earth over radius of Earth. So, so I can calculate it exactly. So my potential energy here, universal gravitational potential energy, can be calculated, uh, and total energy equals to the universal gravitational potential energy. Now to find the escape speed, uh, of course, escape speed is the speed that you have to give to an object on the surface of the Earth and to launch it to infinity. Now, what should I do? My total energy here, so my binding energy, that the energy that holds the object on the surface, is consist of only potential energy. So that's why my kinetic energy that I have to give to uh, object in order to escape from the gravity of Earth and to go to infinity, uh, I should write it in terms of uh, kinetic energy. So let me write it as escape speed 2, and I have the square of this also. Square of this speed, of course, should be equal to the total energy. That's exactly equals to the potential energy. Now, so my MV escape 2 square, of course, over 2 will be equal to the volume that's given here. But I will not take the minus sign because I deal with only with the numbers, you know. So that is g times mass of Earth over radius of Earth. I can simplify the masses here, and you see here that the escape speed here, second escape speed, equals 2 times gme over radius of Earth, and I'll take it to the root of this. Uh, so what's the difference between the escape speed first? We calculate it as g times me over radius of Earth in root, but you see here that I have the 2 here also. So needless to say that I can write it also in terms of escape speed 2, escape speed 1. So if I multiply the escape speed 1, and take it in root here and multiply by 2, I will have the escape speed 2. So what's the difference between the meanings here? Again, the escape speed 1 is the uh, speed that you have to give to an object and launch it to a certain orbit. It won't go away. It just will turn around the surface of Earth, and it's very close to this one. So I can calculate that radius is approximately equals to the radius of Earth. But in this case, when I find the escape speed 2, that's the speed that's needed to give. You have to give to an object to release it and just escape away to infinity. It won't go back here. It will go to infinity, to a far span here. So you can't hold it. So it will escape from the gravity exactly. So if I try to calculate, of course, I can write it also in terms of the gravity here, g times radius of Earth. I can write the escape speed 2 also in these cases here, in these meanings here. Now, needless to say here that I've already calculated the escape speed 1. So let's see it. The escape speed 1 I've already calculated, but it's uh, I lost here. So let me write it in terms of gravity here. I will multiply 2 by 9.8 and I'll multiply by 6.4 times 10 to the power 6 and I'll take it from root. So 2 times 9.8 and times 6.4, I'll have 125, 25.44 times 10 to the power 6 in root. So that will give me the escape speed 2. So if I take it off root, I'll have 10 to the power 3, of course. I will deal with the powers. So the power will be divided by 2. So 125.44 in root will give me 11.2 meters per second. So that is 11,200 meters per second. If you give to any object that is placed on the surface of Earth, it will escape to infinity. I can also write it in terms of kilometers. So 11.2 kilometers per second is the escape speed that's needed, that you have to give to an object that's placed on the surface of Earth to escape from its gravity and to go to infinity. So that's the only difference between the escape speed 1 and escape speed 2. Now, if you look at the table 14.3, that I took sorry from the another book that's called the survey. You may find it also. The escape speeds from the surface of the planets, moon, and sun. You see here that every planet has got its own escape speed. So the escape speed here, indeed, is the escape speed 2, second escape speed, to escape from its gravity. So the general formula for all these planets, the escape speed 2, is g of this planet, gravity on this of this planet, times 2 and times its radius and root. So you may calculate these values that are given in the table by using this formula, or the formula that is more bigger, that is g times mass of Earth, of that exact planet. Sorry, I made a mistake here. Sorry, the gravity times the mass of planet and over its radius. You may find it also by using this formula. So these are the same values again. So the escape speed 2, or the escape speed that is given in this table, is uh, the speed that you have to give to object to just escape from the gravity of this planet. Okay, I hope that you understand. Now that is very easy question. I'll leave it to your own. I hope that you can calculate the mass of satellite or spacecraft is given. It's not important, 5 times to the power 3 kilograms. Now you have to find the escape speed. Here that's denoted as escape speed 2. You have to find the escape speed 2. Uh, and you have to calculate the kinetic energy. I hope that you know the kinetic energy formula that is, kinetic energy I will denote by EK. That is mass of this satellite here, or the spacecraft, that you have to multiply by escape speed 2 square, and over 2. So you may calculate your own. The second thing, I will give it to you own also to solve this problem. We have determined the escape speed velocity for rocket on the far side of the Ganymede, the largest of the Jupiter's moon. The radius of Ganymede is 2.64 times 10 to the power 6, and its mass is 1.495 times 10 to the power 23. The mass of Jupiter is 1.9 times 10 to the power 27, and the distance between the Jupiter and Ganymede is 1.071 times 10 to the power of 9. Be sure to include the gravitational effect due to Jupiter, but you may ignore the motions of the Jupiter and Ganymede as they revolve about the center of mass. Now, what you have to do, of course, the Ganymede and the speed of this, they are revolving around it. The speeds here, let me write here speed 1 and speed 2, they are equal. You might calculate them. You might calculate them. So why do we need the speeds here? Because it has got, the sorry, the satellite here the rocket has got three kinds of energies here, three energies. Total energy of rocket has got the potential energy one that is between the rocket and between the Ganymede here, and plus the potential energy. Well, of course, you have to calculate in terms of minus here, and potential energy too, because it has got the potential energy between rocket and Jupiter. And the third energy, that's the energy, kinetic energy of this rocket, because it revolves with the Ganymede here around the Jupiter. So these two velocities are the same. You may calculate it so that that will be the kinetic energy of the rocket, that is m of this rocket, v2 square over 2. So you may calculate it also. And this total energy, you have to equalize with the escape energy or escape kinetic energy to find the escape in the escape of this rocket here. So when you calculate the total energy, you have to equalize it with the kinetic energy of the rocket, so you'll get the right answer. Thank you. Let's call it today, but let me write a summary. So the total energy of any object that is placed is can be calculated between the potential energy and kinetic energy of this object. So the escape speed 1 is the speed that you have to give to an object to keep on a certain orbit, or sorry, orbit close to this planet. And what's the difference with this escape speed 2? So escape speed 2 is the speed that you have to give to escape from gravitational or from gravity of this planet, of the given planet. So to escape to infinity. So the escape formula, the escape speed 1 is the g times mass of the planet over radius in root. I'm going to write it also in terms of here. I'm going to write it in terms of also gravity. That is gr in root, and the escape speed 2. That is if I take it in root, I have the 2 here and times escape speed 1. That is g times the mass of this planet times 2 and the radius and root, or I can write it in terms of gravity also, 2 times gravity times radius of Earth, and you may take it in the root so that you have the escape speed 2. So that's called escape speed and the difference between the escape speed 1 and escape speed 2. So if you solve the problems, let me know for the problem example of 14.8, and you may solve also the second problem or example that's given in this presentation. Thank you very much. Let's go today.